Okay, here we go. Section 12.5, which turns out to be kind of heavy. So let's look back a bit first and then go forward. All right, game. In R2, which is the Cartesian coordinate plane, lines are defined by a point and a given slope, right? So we say a line, if a line has a slope 2 and some point on there 0, 1, which happens to be the y-intercept, it gives us the equation y equals 2x plus 1, right? So point being, in R2, lines are defined by a point and a slope. In Calc 3, we mostly work in R3, 3 space. In R3, a line is determined by a point, just like up here, and a vector. Right, because what does a vector do? A vector gives, in 3 space, or any space, but in 3 space in particular, it gives direction and magnitude, and all we need is a direction. What's the magnitude is infinity with a line, right? So we're trying to get to the equation of a line in 3 space. And to get there, we go, okay, suppose cap L is a line in R3 through some point which we'll call P naught, and P naught has coordinates x naught, y naught, z naught. So here's our point to go along with the point slope form, and this line is parallel to some given vector v, which we'll write as v1i plus v2j plus v3k. Right? So we have a given point, p naught, and a vector that the line through p naught is parallel to v. And this should be enough to give us the equation of a line in 3 space. Right? And so the line L is the set of points P, so they have coordinates x, y, z, through the vector P naught P, which is parallel to the given vector V, okay? And so here's the picture. There's x, there's y, there's z. Here's my line L. It goes like this. It's just, I'll make it as thick as I can and still be a line. So here's the line, cap L. And we're trying to find the equation of this line, and this thing is floating along through 3 x, y, z space, right? So on this line is a point P naught with coordinates x naught, y naught, z naught. And this line L is parallel to some vector. The vector could be anywhere, but just because these are nodes, I'm going to put the vector down here, and the vector v. And this vector v is parallel to this line, right? And so points on the line, P, and these P's move all the way up and down from infinity to minus infinity. P naught's fixed, it's the point that's given, but these are all the other points. And so, okay, this vector P naught P, I'll put over here, this vector P naught P is parallel to V. Okay? And more importantly, the line through P naught P equals all the multiples of TV, of V. So for all these T, so you take any T and you multiply it by this vector V, it's going to be equal to P naught P, because they're parallel. And T runs between the numbers minus infinity to infinity. T is a parameter. Okay? It doesn't get an axis, it just runs things. Okay, so working with this equation, which came from the picture, we have the vector P naught to P, which is equal to the vector V multiplied by this parameter T. Okay? So P naught P has the coordinates x minus x naught I plus y minus y naught j plus z minus z naught k. And this guy is going to equal t times the vector v, which we defined before as v1i plus v2j plus v3. Okay. Okay, if you run this thing out and distribute the x minus x naught, the y minus y naught, and the z minus z naught, what you wind up with is xi plus yj plus zk, these are all vectors, equals x naught I plus y naught j plus z naught k plus t times v1 IV, which is TV. Okay, so what we're going to do, so this is a vector. Okay, x naught, y naught, and z naught are given. So this vector x naught I plus y naught j plus z naught k, we're going to call the position vector r naught. R naught, which has coordinates x naught, y naught, z naught. Okay. And this is going to be what? Plus TV. And this is now what? The equation of the line, L. Sorry, this is the vector R of t. Okay. So this leads to the definition. The vector equation for the line L through the point P naught, which has coordinates x naught, y naught, z naught, parallel to the vector V, it's the vector r sub t, the left-hand side of this equation, which is equal to r naught plus t of v. And r naught is a vector, it's a position vector of the initial point. And t runs from minus infinity to infinity, it's a parameter. Okay. And if you write this parametrically, so the equation of the line, the x coordinate is x naught plus t v1. The y coordinate is y naught plus t v2. And the z coordinate is z naught plus t v3. Okay. Now, let's be crystal clear here. This is the column vector r naught. And this is the vector v. So all we've done is written r sub t, which is x, y, z, as the sum of the position vector given by r naught plus this parameter times v. And the parameter runs from minus infinity to infinity. Later on, we'll have line segments where it's not infinity, so t will run from -1 to 1 or 0 to 2 or whatever. But for now, that's what we have. And this is how you define a line. So this is L. L equals this whole thing. It's the x, y, z such that this is true for t is part of that. Okay. And parametric equations are complicated. Some schools in high schools teach them. For example, a classic one is if you let the points x, y be the ordered pair cosine theta, sine theta, right? So now theta is your parameter. Instead of t, we have theta, and let's say theta runs from 0 to 2 pi, right? So your x-coordinate here is all the values of cosine of theta from 0 to 2 pi, and the y-coordinate are all the values of sine theta from 0 to 2 pi. And what this parametrization gives you, but the parameter now is theta, is the unit circle. Okay, so that's a lot to take in. Let's look at some examples here, at least one. So 12.5 example. Find the parametric equation for the line L through the point -2, 0, 4, parallel to the vector v, which is 2i plus 4j minus 2k. Okay? So this L is going to have an x, a y, and a z coordinate. So the first term is just the point that we're given, which is -2, 0, 4. And then we take our parameter t and multiply it by the slopes of each component of the vector. So this is 2t, 4t, and minus 2t. Take it from here, here, and here. And that's it. That's the equation of the line. But it's parametrized, and it's important to say that t runs from minus infinity to infinity. All right, let's do another example. Because now it's just applications. All right, so here we're going to find the parametric equation of the line L through the point 2, 3, 0. That is perpendicular to the vectors u equals I plus 2j plus 2k, and v equals 3I plus 4j plus 5k. Right, so now we have to do some thinking here, okay? For the parametric equation of a line, we need a point, which we have. So we have half our battle, and we need a vector that's parallel to the line we're looking for. All right, so we need some vector v that's parallel to the line we're looking through this point. We don't have that, but what we do have are two vectors that are perpendicular to this line. Hence, we need a vector that is orthogonal to u and v. And this will be parallel to the line that we're looking for. So first we need to find this vector that is orthogonal to u and v. And, okay, this is a nice, clever setup. How do you find a vector that's orthogonal to two vectors? You take the cross product. So we're going to call it w. So we're going to let w be the cross product of u and v. And after some work, you have to do the ijk matrix multiplication thing. You get the vector minus 2i plus 4j, minus 2k. Okay, so I skipped a huge amount of computations. So u cross v, you put ijk, and you put this guy for the second row, and you put that guy for the third row. You do all the matrix calculations, and you wind up with this vector w. Now, w is perpendicular to u and v. It's parallel to the line we're looking for through 2, 3, 0. So now we have the vector that we want, right? So the definition of a line in three spaces, you need a point and a vector that's parallel to the line you're looking through the point. Okay, so here we go. X is going to be 2 minus 2t from that guy. Y is going to be 3 plus 4t from that guy. And z is going to be 0 minus 2t, so 0 minus 2t from that guy. And here t runs from minus infinity to infinity. Okay, so that's where I'm going to stop for this video. There'll be another one on Friday to finish section 12.5. And tomorrow in class we will talk at length about how to find lines and stuff. And this is the last part of homework 2. It's section 12.5. 3, 9, 23, and 29. So what I think homework 2 involves section 12, 3, 4, and 5. So and this is due Monday.